So good afternoon, everyone. So we have Professor Shoichi Fujimori. He will continue his third talk on zero mean curvature surfaces in Lorentz Minkowski space. Over to you, Professor.
Thank you very much for the introduction. So in my talk, is about zero mean curvature surfaces in Lorentz Minkowski 3 space. And in the first day, I will give a definition of maximal surfaces, which is space-like surface with zero mean curvature. And then brief introduction of the theory of such surfaces. And the second day, I will give a talk. I gave a talk about non-orientable space-like max spaces. And today, first, I will show some examples of maximal surfaces, space-like maximal surface with fold singularity, then extend to the time-like minimal surface. So in such a way, we have zero mean curvature surfaces, which has some part of space-like and some part time-like. So mixed type surface, zero mean curvature surfaces in Lorentz Minkowski space. Okay. And now, but first we again recall the theory of minimal surfaces in R3. And so in this week, many people already mentioned about the wireless representation. But in my talk, again, let M a Riemann surface and G and eta a pair of meromorphic function and holomorphic one form. And so that this becomes a positive definite Riemannian metric on M. And then define the small f by path integral of this C3 valued one form and take real part. This gives a minimal surface. That is surfaces with vanishing mean curvature in R3. And G, the pair, G and eta, the wireless data, and this G is called the Gauss map of the surface. And since we take the wireless path integral in the wireless representation, so if M is not simply connected, F might not be well defined on M. So to consider the period problem, we set this period of F as follows. Okay. So the path integral with respect to a loop. And then this period of F is 0. This is just the 0 vector. Then F is well defined on M. I mean, single valued on M. And if there exists a non-zero vector in R3 such that the period of F is a subset of this set, this is can be considered as a one-dimensional lattice, then M is singly periodic with this direction. And F is multi-valued, but if we consider the ambient space as R3 modulo this lambda 1, then F is well defined in this ambient space. Okay, and singly periodic surface is sometimes the surface with screw motion invariant is also called singly periodic, but in my talk, such a surface is not appeared, so we just define this way, singly periodic surface this way. And if there exist two vectors in R3 which are non-linearly independent, such that the period of F is contained in this two-dimensional lattice in R3, then F is doubly periodic. And F is again not well defined, I mean, not single valued, but if we consider the ambient space as R3 modulo this gamma 2, then F is well defined in this space. Okay, and the same way, if there exist three vectors, linearly independent vectors, V1, V2, V3, such that the period of F is a subset of this three-dimensional lattice, then F is triple periodic. And again, if we consider F as a map into this R3 modulo gamma 3, this is equal to three-dimensional torus, then F is well defined. So now, let me show some example. Okay. Define M as a hyperelliptic Riemann surface, compact Riemann surface of genus 3, which is defined by this hyperelliptic curve with a parameter A. Parameter A is parameter between 0 and 1, real parameter. And then we set z equal to z, and eta is dz over w. And then we have Schwarz P, which is appeared in many talks in this conference. But here we have one parameter family of Schwarz P surface. And if if A is this value, square root 3 minus 1 over square root 2, this is almost 0.52 or something, then this is the most symmetric case. So we have this surface. Okay? And you see, we don't draw the three-dimensional lattice, but maybe you see the lattice. So this part and this part front and back are identified, and the left-hand side and right-hand side are identified, and top and the bottom are identified. So we see front and back identified, left and right, and the top and the bottom. Then we have genus 3, compact genus 3 Riemann surface. Okay. And this is most symmetric case, and we have line segment here and symmetry plane here, okay, and so on. And if A getting smaller and smaller, then the surface looks like this way. And in this case, the surface looks like this. Okay? So we have tiny catenoid neck. So it looks like too many planes, horizontal planes connecting by tiny catenoidal neck. Right? And A goes to bigger than bigger, then this and top and bottom becoming like a square shape. Okay? So and the surface looks like this. Okay? In fact, Schwarz P surface has 5-dimensional family, but this is only one parameter family in that 5-dimensional family. Okay, so this is Schwarz P family. And also, we have Schwarz D family. We take conjugate surface. So we have same M, same MA, and same G. But eta is different. Yeah, we multiply here I. So we have another family of triple periodic minimal surfaces, which is called Schwarz D surface, which is also appear in this conference many times. So in this case, we have this kind of surface. So it is now not easy to find this is genus 3 surface, but actually this is genus 3. Okay. And then if A is close to 0, then the surface looks like this. Okay. So here in the center, we see some kind of helicoidal shape here. Okay. And if A is close to 0 or close to 1, then the shapes look like this. Okay. So these are Schwarz D family. Okay, and let's think about the limit of these surfaces. Okay, now limit of these surfaces as A tends to 0. Then what happened? So this is Schwarz P surface with A equal to 0.1. And since this is triple periodic, so, and this here is the lattice. I don't draw the lattice, but you see the lattice. And this part can be shifted to here. If you can shift this here, because this is triple periodic, so just translation is okay. So, and also this part can be shifted to here, okay? Yeah. And this part can be shifted to here. And this part also we have vertical symmetry, vertical translation. And then after suitable translation, so this surface is exactly the same as this surface. Okay. Now you see there are two catenaries connecting here. Right? And when A goes to 0, then these two catenaries getting far away. And finally, we have catenate as a limit. Okay. But maybe we need to dilation, with suitable dilation. We have catenoid, so we have two catenoids. And also, Schwarz D surface, okay, this surface. And then again, I don't know what to do, but again, some suitable translation. Maybe this part goes to this part, and so on. Then this surface and this surface are exactly the same. Just different places we cut the surface. So as we see the talk on Monday, Professor Kami talks, we see the surface looks like two helicoids connecting here, and the surface looks like a parking lot. Okay. And when A getting closer and smaller and smaller, then these two parts are getting far away. And finally, we have helicoid. Okay, so as a limit, we have helicoid and catenoid. Okay, so this is one example. And now this is a limit for A tends to 0. On the other hand, the other limit, when A goes to 1, so again, so this surface is now is 0.9, and okay, this part corresponds to this part, and this part we can translate to here, then become this part, okay, and this part is this part, and this part being translated to here, then we have this. So this surface is the same as this surface. Okay. So, and then when A get 1, then these two parts getting far away. And we have a surface, Shark's tower, yeah, connecting with this end. Yeah. So this is singly periodic surface, Shark's surface. Okay. So Shark's surface, Shark's tower, this is end. So this goes to infinity. So this is also end. This is end. So we have 4 ends. But vertical direction, if we translate the surface, then this part and this part can be identified and much analytically. So this is singly periodic, vertical direction. And also the conjugate surface, Schwarz D. This is already looked. Oops. I'm sorry. Yeah. The surface already looked like two shark surfaces, doubly periodic shark surface connecting at the end. So, and really, if we take the limit, you have shark surface. Okay. And this surface is doubly periodic. So here we have many vertical lines, and one can reflect by rotating 180 degrees with respect to these lines. Then the surface extends analytically. So we have a doubly periodic surface, okay, horizontal way. So but this is the end of the surface. So this can go infinity. So the bottom also ends. So we have top ends and bottom ends, and the surface is doubly periodic. Okay. So this is a limit. Also, so now we consider non-periodic surface. So we have seen the periodic surface Schwarz D and shark. But here, this is non-periodic surface called George Meeks enoid. And George Meeks enoid, for n is greater than or equal to 2, we can set the wireless oscillator this way. So in this case, the picture shows the n equal 5 case. And n equal 2, we have catenoid. So here, now we have Riemann sphere minus 5 points here. Okay, so on the equator, we remove 5 points. Okay, and then after using this wireless oscillator, we have this George Meeks surface. Okay. So this is topologically sphere minus 5 points. And so we have 5 catenoidal ends. Okay. And you see the surface has self-intersection. So surface is not embedded. But if we consider if we restrict the domain as near the end, then it looks like the half of catenoid. So the end is embedded. Okay, end is embedded, but the surface is not embedded. Okay, you see. Okay, this is George Meeks surface found by George and Meeks in 1980s. And also we see Karcher saddle tower with 2 n ends, which is singly periodic. And again, when n equal 2, it is Shark's tower. Okay. So the graphics show n equals 3 case. We have 6 ends. So the domain is a sphere minus 6 points. So 6 points located symmetrically on the equator. Okay. And then after taking wireless data, we have this Karcher tower. So this equator corresponds to this part, horizontal. Okay. But then the end, this half of circle, northern half of circle, corresponds to this curve. This curve, okay? The southern half of the curve corresponds to this curve. Okay? So this is the end. The end looks like vertical. Okay? And then again, so this part corresponds to this part, and this equator corresponds to upside this part or this part. Okay. So and these upper curve and lower curve can be identified because this is single periodic. Okay. And then this half of circle again describes this particle, almost particle ends. Okay. So in such a way, we have minimal surface, single periodic minimal surface with 6 ends. Okay, 6 ends. So 1, 2, 3, 4, 5, 6. And the vertical direction, the translation invariant. So we have a single periodic minimal surface. Okay. And this is most symmetric case. So end is located symmetrically. But one can move the location of ends in this way. So we can deform this way. So when phi is pi over 2n, yes, the surface is the original curvature tower. And phi is getting smaller than the symmetry breaking. And so the ends located this way. Okay, so the surface looks like, in this case, so surface looks like this. Okay. It is still embedded, but so this is the limiting case of embeddedness, embedded surface. So because this end and this end becomes parallel, so we have now 3 pairs of parallel ends. Okay. And if phi is smaller than this pi over 4n, then surface has self-intersection. Okay, so now in this case, this ends intersect. So, but if we restrict the domain to near the end, then it is still embedded. So it has embedded ends, but the surface itself has self-intersection. Okay. And it looks like George Meek's surface, right? Okay. So, and as a limit, we have George Meek's surface. So the phi goes to 0, then we have George Meek's surface. Okay. George Meek's enoid. So this is phi is very close. Then finally, but this is single periodic, then this is not periodic. Okay. This is George Meek's surface, enoid. Okay. Now, okay, so we move to the subject to our Lorentz Minkowski 3 space. So these examples we will see later as a maximal surface or zero mean curvature surfaces in L3. Okay. Now L3, again, the Lorentz Minkowski 3 space with this inner product, indefinite metric, but non-degenerate symmetric bilinear form. And again, F is space-like if the induced metric is positive definite. And F is called the space-like maximal surface if the mean curvature is vanished. Mean curvature vanishes identically. And in this setting, we have the y-axis type representation. So again, so this is, let M be a Riemann surface, and G and the eta are a pair of meromorphic function and holomorphic one form, so that this holds. Then this F gives maximal surfaces in L3. So the difference is here plus, minimal surface case here is minus, and here is plus. Okay. And G and the eta are called wireless data. And G is also called Gauss map. Okay. And it is known that the only complete maximal surface is a space-like plane. Okay, so I said this maybe third time. So compare with the same wireless data to the minimal surface in L3 and maximal surface in L3. So let M be a complex plane and G equal to Z and eta equal dz. So in this setting, in R3, we have n-path surface, okay, n-path surface. So n-path surface is symmetric with this plane here and with this plane, and we have two lines, horizontal lines. So this is symmetric, okay. So the number of symmetry group, order of symmetry group is 8. Okay. So and in the same data, as a maximal surface, we have this surface. It's very different. And so this is singularity, singular set. So from top of view here is we have a singular set. Okay. And these 4 points are called swallowtail. And between the swallowtails, we have 4 cuspidal cross gaps. This part, this part, this part, this part. And the other singularities are cuspidal edge. Okay. So, and as I mentioned before, generic singularity of maximal surfaces, max face, is these 3, cuspidal edge, swallowtail, and cuspidal cross gap. So all of 3 appears in Lorentz n-path surface. Okay. And next, consider the catenoid. Let M be a C minus 0, and G equal to Z, and eta is dz over Z squared. And as a minimal surface in R3, we have this catenoid. So, and the profile curve is hyperbolic cosine, the Cauchy curve. Okay. So rotate, surface of revolution. But as a maximal surface, this is again a rotational invariant surface of revolution, but the profile curve is Cauchy curve, hyperbolic sine curve. So we have this surface, and in the center, it is called cone-like singularity. So this is not generic. And also, helicoid. So the conjugate of catenoid is helicoid. And consider this helicoid. As a minimal surface, it is helicoid, and it is a ruled surface. We have vertical line here, and then also horizontal lines. Horizontal lines. We see helicoid here. So, what happened for the conjugate surface of maximal catenoid is maximal helicoid. Okay, so it looks this. Okay. So it doesn't seem there exist singularities, but actually this helix is a singularity. So inside this helix, this is singularity. Outside is just end. So if we draw more near the end, then this can be bigger and bigger. But inside, we cannot go enter inside because the tangent plane is already 45 degrees. And if we want to go inside, then the surface becomes time-like. So as a space-like surface, we cannot go enter. Okay. So this is called the fold singularity. And this part corresponds to the unit circle in the domain. And outside of circle and inside of circle, we have now 2 to 1 map. So this is really fold. Okay. So this happened. And also, as some people already mentioned, but let me recall one more time. Okay. Let F maximal surface is wireless data. Actually, this is max face. Maximal surface is wireless data, G and eta. Then we can take the conjugate. Conjugate surface means the wireless oscillator G and I eta. So we have same G and same M, but eta is different. We multiply by I. Then we denote this surface by F star. And F star is a conjugate surface. Okay. And by applying the criteria of singularities, we see that if F has capital H at P, then F star has also capital H at P. Okay, so capital H is invariant under taking conjugate surface. But if F has a swallowtail at P, then the conjugate surface has capital cross cap at the same point. And also capital F has capital cross cap at P, then F star, the conjugate surface has swallowtail. Okay, so swallowtail and capital cross cap are dual each other, conjugate each other. Also, if F has convex singularity, then the conjugate surface at P has fold singularity. And vice versa, F has fold singularity at P, then F star, the conjugate surface, has convex singularity. So the conjugate convex singularity and the fold singularity are conjugate each other. Okay. So capital H is invariant, and swallowtail capital cross cap are conjugate, and conlike and fold singularities are also conjugate. Okay. So okay. So the conjugate. So this point is in the domain. This is the unit circle. Unit circle shrinks to one point here, and unit circle goes to this and single periodic. So this is not closed curve anymore. Okay, so now let's see the maximal surfaces with the data of Schwarz surface. Okay, and Schwarz P surface, we have many catenoidal neck, but then we have the maximal surface. We have many cone-like singularities here. Okay, so now we lose some symmetry. So this value has no meaning anymore. This is one of, so in minimal surface case, when A equals this value, then symmetry group increasing, but in this case, no, not increasing, but okay. So and if A close to 0, then the surface looks like many horizontal planes connecting catenoidal neck, I mean, cone-like singularities. Okay. So which appeared in her talk in the morning. And A is close to 1, then the surface looks like this. Okay. So now the surface is space-like. We cannot stretch the surface. So, but now this is not line, but this looks like really line, very close to line, and the 45-degree angle. So this is almost a limit case. Okay. This cannot be vertical because the surface is space-like. Okay. So also, and the conjugate, so we again have fold singularity. Surface looks like this. So here, this fold singularity surface, okay? Fold singularity. And this is a line, horizontal line, and we can extend by rotating the surface with respect to this line, 180 degree. So we have a singular curve for the singularity here, and here, and here, and here, and here, and here. Okay. And when A close to 0, then the surface looks like, sorry. So surface look like more horizontal plane. Okay. And here, this is hold singularity, and also these are hold singularities. Okay. And A is closer to 1. So the surface getting thinner and thinner. Thin. And it looks like a very small, thin surface. But the symmetry group is the same. Okay. So these are the fold singularities. Okay. And now consider the limit. Again, Schwarz P case, this surface is the same, exactly the same as this surface, but after a suitable translation. Okay. So we have this surface. So this is A equals 0.1. And then as a limit, we have catenoid, maximal catenoid. Okay. And also Schwarz D case. So this surface is exactly the same as this surface after a suitable translation. And the surface looks like this. Okay. And as a limit, we have 1/2 of this surface. Okay. And this is helicoid again. Okay. So we have this example. And the other limit, and now A equal to 0.9, and after a suitable translation, this is exactly the same as this surface. Okay. And now, this is almost right-like line. This is not, but this is very close to the right-like line. Okay. And after taking limit, we have this surface. Okay. So this is cone-like singularity, and this is cone-like singularity, this is cone-like singularity, and this is the end of the surface. Okay, this is the end of the surface. But end does not go to infinity, so end still remains finite. Okay. Something strange happened. Okay. So this surface, as a minimal surface, shark surface is doubly periodic and the conjugate is singly periodic. But in this case, this surface is not periodic, and this surface is triply periodic. Okay. Triply periodic, but has end. Okay, that's a bit strange. Okay. So this triply periodic, but the end does not go infinity. Still remain finite point. And also, the conjugate surface, as a limit, we have this shark surface. And this is, again, this is not periodic. Okay? So this is end of the surface, end. So the surface has 4 ends and 4 fold singularities. Yes? Yes. Yes. Okay. So this is end of the surface. So this is 1 point in the domain. So this is maybe 1/4 of the circle. Yeah, goes to 1 point. So in the domain, this is curve, but in the ambient space, it's 1 point. And here corresponds to 1 point in the domain. So this goes to the straight line. Yes. So something strange happened here. Okay. So also consider George Meeks type maximal surface. We have okay. So for the singularity again. So let for n equals greater than or equal to 2, we have this kind of surface. Okay, this is n equal 5 case. So we have this surface. So this is for the singularity. This is also, so we have 5 for the singularity, 5 components for the singularity. And this is the end of the surface. So if we draw more wider domain, then this goes to infinity. Okay. So somehow catenoidal shape collapse. So we have 5 components for the singularities. Okay. And yeah, and n is bigger. It looks like very this right cone has nothing, but just I would like to make sure that the surface is very asymptotic to this cone-like this cone, right cone. This is n equal 17 case. So yes. Has no self-intersection, right? Yeah, but yeah, okay. So, but inside of the circle and the outside of the circle, so at the same point. So that means 2 to 1, so not embedded. But yeah, if we restrict inside the circle, then this is no self-intersection. Yes. Okay, so in this case, also this surface has each singularity is for the singularities. Okay, now, so we consider the for the singularities. Okay, now the easiest example is helicoid, maximal helicoid. So the surface, maximal helicoid looks like this. Okay. And this outside is the end of the surface, so we can extend it as much as we want. But inside, we cannot go enter as a maximal surface, as a space-like surface. But since maximal surface is described by complex analytic function and taking real part, so this is a real analytic function. So somehow, anyway, we can uniquely extend the surface analytically. So what happened? So we extend the surface. So we got this. Okay, so black part is the extended part. Okay, so this part is a time-like surface. But then time-like surface, we can take space-like unit normal vector field and define first fundamental form, second fundamental form, and compute the mean curvature. Then the mean curvature is still 0. Okay. Then again, we have a boundary here. So we cannot go further as a time-like surface. If we go further, then again space-like surface. But then we can extend, more extension. Finally, we have this. Okay. So and this is exactly the same as minimal helicoid in R3. So this is, and the white part is space-like maximal surface, and inside black part is time-like minimal surface. So this is embedded zero mean curvature surface with no singularity now. Okay. So mixed type zero mean curvature surface in L3, and which is exactly the same as minimal helicoid in R3. Okay. And also we start from shark surface. So it is not periodic, and 4 ends, and for the singularities. And after we extension, we have this surface. Okay, now, yeah, sorry. So the outside is black part, time-like part, and the inside is space-like part. And in this case, we have entire graph. Okay. So as I mentioned before, as a minimal surface in R3, entire graph must be a plane. And also maximal surface, entire graph must be a plane. But as a zero mean curvature surface of mixed type, we have this example other than plane. Okay. So now I want to introduce something about time-like minimal surface. Let F be a surface in L3, and F is called time-like surface if this induced metric Lorentzian. And then F is time-like minimal surface if the mean curvature vanishes identically. Okay. In this case, maximal surface is really area maximized, but in this case, we have no such a property. So I don't know if the minimal surface is good naming, but just mean curvature equals 0. So I borrow the name from minimal surface in R3. So this is not minimal anymore, but yeah, we say minimal, okay? Because this is the zero mean curvature. And graph of a function t equal phi of x and y in L3 is space-like maximal surface if and only if phi satisfies this equation with this inequality. And graph is time-like minimal surface if the phi satisfies the same equation with this inequality. Okay. So thus we called this equation as a zero mean curvature equation. And the graph satisfying this equation without this inequality is called the zero mean curvature surface in L3. Okay. Now, we'd like to make extension of maximal surface to zero mean curvature surface. Okay. So there's a way to make such a zero mean curvature surfaces from null curve. Okay. So regular curve sigma in L3 is called null curve if sigma prime is right-like vector for any p. Okay. So and null curve is said to be non-degenerate if the first derivative and second derivative are linearly independent for any p. So the velocity and the acceleration are always independent. And then in this setting, this theorem is known. It is first proved in Gu in 1980s, and then later Creatine showed in 2003. Let F be a maximal surface with fold singularities. Then, and gamma, a set of fold singularity of F. Then the composition of this gamma, this is a curve in a domain. So the composition of gamma and F, this is a space curve. This curve is non-degenerate null curve. And we define F tilde as a center of this gamma of mu u plus v and gamma of mu u minus v is really analytically connected to the image of F along gamma as a time-like minimal surface. So we have maximal surface as fold singularity. Then the fold singularity is a non-degenerate null curve. And with this formula, we parameterize non-degenerate null curve. And by this formula, we have extension, okay, the surface. So in such a way, we have zero mean curvature surface of mixed type. Okay. So we have Schwarz D-type maximal surface with fold singularities, as I showed before. And so we extend this surface as a zero mean curvature surface. Okay. So then after extension, we have this theorem for any A, the parameter, sigma A oriented close to manifold of genus 3 and 3-dimensional lattice, so that, F is a surface zero mean curvature embedding into this torus. Okay. So the extension is just we apply the Creachin and Gou's theorem, and we can observe the symmetry. It has the same symmetry as the minimal Schwarz D surface in R3. So it is easy. So the remaining is embeddedness. Embeddedness is quite difficult. So how to prove the embeddedness is as follows. So this is a fundamental piece of the surface by symmetry. Okay. So look at the surface from the top of view. Then the surface looks like this. Okay. So this part is time-like minimal. This part time-like minimal. This part is a space-like maximal. Space-like maximal part. Okay. And we show that the fundamental piece is contained in a prism over a triangle. And triangle is, so this is equidistance, and this is right angle. So this special triangle, prism over this triangle. And first we showed this, and then okay. And each height, we cut the surface by horizontal plane. Then intersection, we see that there is a curve, and which is not has self-intersection. So in such a way, for each level, we can see the curve, embedded curve. So we have embeddedness over here. And then after suitable reflection, okay, so this is fundamental piece is inside the prism. So after reflection, the prisms are not intersect each other, has no intersection each other. So we can see the surface is really embedded. Okay, let's see the. So we have straight lines, and we can extend the surface by reflection. I mean, rotate the surface. So then we have this. Now we have this surface. And this space-like part has a symmetry property. So you see this curve is in a planar, one plane, vertical plane, and intersect vertically, perpendicularly. So we can make reflection, extend by reflection. Okay. So now we have this surface. Again, so finally we have this surface. Okay. So this is Schwarz D surface. The topology is really same, and symmetry is also same. Okay. And yeah, after making reflection infinity many times, so we have Schwarz D surface. So which is genus 3, topologically compact genus 3 surface, and which has the same symmetry to the minimal Schwarz D surface in R3. Okay. So we have one parameter family of embedded surface, periodic zero mean curvature surface. So, and when A is close to 0, then almost part is space-like. So only a small time-like part. But then A is getting bigger and bigger, and then the space-like part is getting thinner and thinner. Almost all part is now time-like. Okay, also, we can consider the limit. Now, this is equal to 0.1 case. And this surface is exactly the same as this surface, as we see before. So this part, okay? So this is similar to minimal Schwarz-D surface in R3, but different, a bit different. Okay? This is maximal in L3. And the we see before is minimal in R3. But then the limit, we have the same limit. This is the limit is exactly the same as minimal helicoid. Okay. And the conjugate surface, the other side, when A goes to 0, as a minimal surface, so we have the doubly periodic shark surface as a limit. But in this case, the white part is space-like surface, so cannot become like the tangent plane cannot be vertical. So can be only 45 degrees. So the surface looks really different to the minimal surface in R3. And as a limit, as a minimal surface in R3, we have doubly periodic shark surface, but in this case, non-periodic surface, entire graph instead. Okay. And yeah, we have another example. We start from Schwarz H surface. Yeah, there is a surface called Schwarz H surface. This is also minimal surface, triple periodic minimal surface in R3 of genus 3. And with this data, so we have this surface. So we have convex singularity again. Okay. And if A is close to 0, then the surface, again, horizontal planes connected catenoidal neck. But the locations are different as before. So because this is a triangle, so before we have square, so the location of the catenoidal neck is different. Okay. So in this case, we have triangle, many triangle shape. And so it has convex singularity. So then the conjugate surface has fold singularities. Then again, we can extend the surface. So then we have this surface as a mixed type zero mean curvature surface in L3. So the white part is space-like, and the black part is time-like minimal surface. Okay, so this surface. And we also have reflection principle. We can extend the surface by reflection. I mean, rotate the surface with any straight line of 180-degree rotation. Okay. So again, A is close to 0. We have this like two tiny horizontal plane connected by catenoid, not helicoid. Okay. So and A close to 1, then we have this surface. So space-like part is getting thinner and thinner, and time-like part getting bigger and bigger. Okay. So we have this surface. Now, the limit of the surface. So, Okay, so A goes to 1. So the limit, so this surface is the same as after suitable translation. This surface is this surface, okay? So in the center we have something, yeah. Something. And this is the Karcher surface. As a minimal surface, it is Karcher tower, so singly periodic, but in this case, it is not periodic. But entire graph, actually. So this is the entire graph. The center is space-like, the outside time-like. And these are ends of the surface. Okay. So we have this surface. So as a limit, we have Karcher surface, Karcher type maximal surface, zero mean curvature surface. Okay. Now we consider other example. Okay, this is a Karcher type surface as we see before as a limit of Schwarz H type surface. Okay. Now we use the same YSS data of Karcher surface as we see before as a minimal surface in R3. Then this corresponds to the phi equals to 1. So there is a deformation of Karcher's surface. So this surface, Karcher's phi equals 1 case, the end is located symmetrically on the equator. And then phi moves, then the symmetry breaking, and when phi goes to 0.5, we have this surface bit deformed. Okay. Okay. So now 2 becomes parallel from top of view. These are parallel and these are parallel. Okay. On this surface. And now it is the limit of the surface as a graph can be represented as a graph. So because this part here, you see the tangent plane is vertical. So phi is greater than 0.5, the surface is a graph. But here we have vertical plane. And then the surface is, the phi is smaller than 0.5, then this is not a graph anymore. So you see, this is not a graph, but still embedded. Okay. Not a graph, but embedded. Okay. And as a limit, we have a George mix type surface, and phi goes to 0. So now we have 6 ends, then now we have three ends. Okay, and this is again embedded, but not graph. Okay, so the outside black part is time-like, and inside the white part is space-like part. Okay, so we start from Schwarz H type surface, 1 parameter family. Then as a limit, we have Karcher type. Then further, we can deform. Then we get George mix type surface. Okay, so we prove that for any number n equal to greater than or equal to 2, the analytic extension of George mix n-noid are properly embedded. That means zero mean curvature surfaces in L3. Okay, so this is max phase, George mix type, space-like. So we have for the singularity here, and these are ends of the surface, And then we can extend after extension. So this is not a graph, but embedded surface. Okay. So embeddedness is a bit difficult to prove. But the outline of proof, because George mix surface, so we can integrate explicitly. So then the integration for any n, we can explicitly write down x first component, second component, third component in such a way, and is equal to r times e to the I theta. Then, yes, we see that if, so we put z equal r times e to the I theta. So we see that this symmetry, f of r and theta is f of 1 over r and theta. So we set u as follows. Then we can represent x1, x2, x3 as follows by using u and theta, where t is first Chebyshev polynomials is a variable u of degree n and n minus 1. Okay, so Chebyshev polynomial. Then yes, so the deformation, so this part, u is bigger than 1 is space-like, corresponds to the space-like maximal surface. And u equal 1, this dashed line corresponds to the fold singularity. And then one can extend this way. Yeah, this part becomes a time-like part. And then, yeah, we can prove the embeddedness of this part. And after reflection, we can say the surface is embedded. Okay. And also, Curvature type surface by using this wireless data. So, yes, in this case, we can prove that this is a graph. Okay. So, of course, embedded, because it is graph. So, it is graph. And this part is the limit the surface can be graph. Surface is graph. Okay. So you see here we have a vertical tangent plane. So if phi is smaller than this value, then this is not graph anymore. So but then, so if, for example, this case the surface is not graph but still embedded. And finally, we have George mixed surface, but it is also embedded. Okay. Okay, now next we consider zero mean curvature graph, entire graph. Okay. So, for example, with these various data and n and phi, we can choose n is any integer, any positive integer, and phi is between real number between these two values. And when n equal 2 and phi equal this value, then the surface is a graph and can be explicitly write this way, log of cos x over cos y. Okay. And this case, t equal to x times hyperbolic tangent y. And these are entire graph. And so this t satisfies the zero mean curvature equation. And the inside here is space-like, outside is time-like. And inside is space-like, outside here is time-like. And these surfaces were first found by Kobayashi, Osamu Kobayashi in 1980s. So we named this entire graph Kobayashi surface. And we consider the generalization. Okay. Let alpha 0 to alpha 2n minus 1 be a real number satisfies this inequality. And we set M as a Riemann sphere minus these points, these two endpoints. And we set N G as G to the G equal G to the N minus 1, and the eta as follows. Okay. Then it is easy to show that the max phase F with the above biases data is well defined on M. So period problem is solved. Okay. So as a minimal surface in R3, the period problem is not solved. But as a maximal surface, the period problem is solved. And the singular set is this unit circle. And the singular set consists of non-degenerate fold singularities. So all of the singularities is fold singularity. So we call the max phase given with this data the order n Kobayashi surface, and these data are the angle data of F. Okay. So we can prove that let the following: let F be an order n Kobayashi surface with angle data alpha 0 to angle alpha 2n minus 1. And consider the analytic extension, and we denote by F tilde. And we set alpha 2n equal to 2 pi. And we can show that if the angle data satisfies these values, and all of them are distinct, then F tilde is proper immersion, so properly immersed surface. And in particular, And so if the angle condition satisfies this, then F tilde is the entire graph. And also, if n equal 2 case, we can analyze the surface more precisely, and all of the cases is properly embedded without the angle condition. Okay. So there remaining the problem. So we see that we can have the condition of the surface to be entire graph and properly immersed. But so between 1 and 2 somewhere, there is a phrase that properly embeddedness holds and properly embeddedness doesn't hold. So, but so far, we don't know where it happens. So the Kobayashi surface, if the alphas are located symmetrically, then entire graph. Then if we modify somehow, then somewhere it is not graph, but embedded. But then further, it is not embedded, but immersed. But then further, it has some singularities, again, as a zero mean curvature surface. So we know the condition about the surface to be proper immersion and the entire graph, but here we don't know so far. So this is the remaining problem. So I hope some of you will solve the problem. Okay. And the n equal 2 case, we don't need any angle condition. So anytime, any case is properly embedded. But the surface looks sometimes really, really weird. Okay, for example, these are alpha 1, alpha 0, alpha 1, alpha 2. All of them are 0, then the surface looks like this. Also 0, 0, 1 pi, we have this surface. It's still embedded, but in this case, it is clearly not graph. Okay. So these are the surface, Kobayashi surface, about Kobayashi surface. So finally, let me introduce some relationship to fluid mechanics. And yeah, we search the zero mean curvature surface equation, then we have we happen to see that some equation is very similar to the equation in the fluid mechanics. So let me introduce. But I'm really a beginner of fluid mechanics, so please don't ask any questions. just introduce the equation. Okay. Consider a two-dimensional flow with velocity vector field v is u and v. So u and v are functions of x and y. Okay. And density rho and pressure p. Okay. And we suppose the following conditions for the flow. One is the flow is barotropic. That is, the pressure depends only on rho, density. Okay? And also, C is defined this dp over d rho, the square root of this dp over d rho is called the local speed of sound. And the flow is steady, that is, the velocity and density, pressure do not depend on time. Okay? And we suppose no external forces. And we also assume that the flow is irrotational because that is the rotation lot of v equal to 0. Okay? So lot is in two-dimensional lot. Yeah. So by condition 2, the equation of continuity is reduced to this. Okay. So thus there exists psi, the function psi of x1, y, so that psi sub x is minus rho times v, and psi sub y is rho times u, and which is called the stream function of the flow. Okay. And then it is known that the stream function psi satisfies the following equation. Okay, rho squared c squared minus psi sub y squared psi sub xx plus 2 times psi of x psi y psi sub xy plus rho squared c squared minus psi sub x squared times psi sub yy equal to 0. So this is very similar to zero mean curvature equation. So if rho times c equal to 1, then this equation is really exactly the same as zero mean curvature equation. Okay. But we asked some expert of fluid mechanics, then such a flow does not exist. So this is some virtual. But so now anyway, we suppose rho, okay, the rho and c are not constant, both are function of x and y. So we cannot suppose in general, but anyway, we suppose this. Then there exists a positive constant rho naught, so that p equal constant minus rho naught, rho 1 over rho. And rho is rho naught times this, and c equal to this. Also, the vector, velocity vector v is equal to this. Okay. And also, then we have this lemma. The speed normal v is greater than c if and only if this inequality holds. And the norm speed of v is less than c if and only if this holds. Okay, so as a result, we have this theorem. Let sigma t be a locally convex curve, and with t and arc length. And then there exists psi, function psi, so that x and y and psi xy is a zero mean curvature surface, because psi satisfies zero mean curvature equation. Which change type across a non-degenerate null curve, xt, yt, and t. That is, psi is a string function of some flow with this condition. This is really an artificial condition, but okay. Then moreover, the velocity vector field of this flow satisfies, the speed tends to infinity as xy approaches to the null curve, locally convex curve. And the flow changes from being subsonic to being supersonic across the sigma. Okay. And also, the acceleration of sigma points to the supersonic region always supersonic region. So we have this theorem, and we don't know it is useful or just a theorem, but yeah, we have anyway this theorem. So okay, and maybe so these are the references. So the first one we constructed Schwartz T-type zero mean curvature surfaces, and the second one is we gave a criterion of fold singularities and so on. And third one is entire graph Kobayashi surface we consider. And then this one is, we focus the surface, George mix type surface, the embeddedness of George mix surface. And the fifth final one is we consider the Schwartz H type zero mean curvature surface and consider the limit. And as a limit, we have Karshal surface, and then further limit, we have George mix type surface. Okay, so we still have some time, but yeah, okay, so thank you very much. I don't know what it is which.
Very nice. Thanks. So are there any questions?
So, sir, like we have seen, like if maximal surface have folded singularity, we can extend it analytically. So, does there exist maximal surface having folded singularity, so we can have extension, and it have other singularities also?
Yes.
There exist.
Other singular might exist.
Might exist.
Yeah.
So if there exists, then how the other singularities are affecting the time-like surface, that extension?
In space-like surface, if one has other singularity in space, then extension after extension. So I don't know what happened.
This is like one question is like when you're using time-like minimal surface, are you using split complex, that paracomplex number here?
This case, I just use U and V, so two real. Yeah. So and okay. Where is that? Yes, I use just this. So no two real values. So. But maybe if you construct from time-like surface, maybe you need paracomplex surface.
Yeah. Thank you.
Okay, so we thank speaker.
Okay, thank you very much.
Thank you very much.